No, that's not gaming. That's not gaming. That's education. Alright. Oh, and the title's wrong. Alright, hello, my name is Alex Kim. My internet heading is Copas. I'm sure some of you might have already known from my Reddit posts. And I'm here to do a technology demonstration on my little desktop setup that looks like a fire hazard. My microphone's above me, so I'm not sure how my microphone quality is gonna be like in the end. But this is my desktop setup. Yeah, it looks like a fire hazard, like I said. And if you open inside it, you'll probably see 3 buck converters. 1, 2 here, 3 here. If you don't know what a buck converter is, it basically chops down electric power, I guess you could say, into a lower voltage and lower current. That's how I run my Peltiers. I'm not sure if I should do a demonstration on how Peltier even works, but I'll do a brief lecture on how they work at the end. So I got 1 here, I got 2 here, I got 3 here. That one's for running the pump to the CPU and the radiator fans. There's actually 3 here, which is connected to the motherboard, and then there's 2 here. So it's essentially a push-pull setup. You kind of gotta do that because it's generating a lot more heat than a normal CPU would. So my CPU, it peaked at 150 watts during a benchmark. It didn't crash, thank God, but it did hit 65 degrees Celsius very quickly. So there's that. So yeah, that's also insulated. Oh, that's about to come off. That's supposed to come off, but I mean, I should probably put tape on it, but later. Yeah, cause condensation forms pretty quickly. That's the direct diaphragm. Thanks to Bauer. That's a really cool product. It's been put with liquid thermal paste, conductors. I tried to put the extreme version, but because the CPU is pretty damn cold, it will actually solidify, and I'm not sure what would happen if that thing starts solidifying, and I don't want to find out. Either way, so 1 buck converter, you can adjust the not temperature, voltage, and the current setting by just pressing this. It's like $35 on Amazon. Right now, I think it uses 100 watts. I know it's a lot. 100 watts a lot. 100. There's another 100. It's like 200 watts. But it drops coolant temperature pretty damn low, even with the CPU loaded. So that's that. Each of these is connected to 6 Peltiers. There's 12 in total. And I gotta set it independently, unfortunately, until I could probably figure out put programming here, so just set it automatically. But I also like this. Everything's inside a case. This neat little thing, so you can move the computer around. I was thinking about using a compressor. Apparently there's already a setup using a compressor, but I exactly don't have a room to put a compressor here, so yeah. That's the LED driver. Yeah, I cut out the product taping, like the product sticker, apart from this side, so I don't forget like the actual rating. Because I had to put extra radiator here, just in case. in case if this thing decides to explode. Uh, that's the remainder of the Peltier block. Yeah, it's too big, so I can't even like put it in there. I was able to barely put it last time, but because of that pump, that's the CPU coolant pump. Does it show on the camera? I hope that shows on the camera. There we go. That runs a coolant pump from the middle of the heat block, the cooler block, water block, into the CPU. And I'll show you what the actual setup looks like. That's my last setup. So essentially the same thing, except that one has 12, this one has 8. You got a radiator here, which is transferring heat from the hot side. So there's Peltier in between here, you can see that. Cold side touches the middle of the heat block. That gets pumped with this. I'm not sure if I have to put that or not, because this is also an AIO pump, so it has a pump on its own, but hopefully that increases pressure, so I think that increases pressure a little bit more. But yeah, hot side also has a pump. I mean, you kind of need that. It's a water block, so it needs to circulate coolant. That goes to radiator. That cool radiator gets mounted to the front of the CPU. I mean, the front of the desktop, like that, and it gets cooled. Literally, basically how a normal water cooling setup works, except you got this as a heat exchanger. That used about 80 watts, I think, and it keeps my CPU at fairly stable temperature. I think 5.75 gigahertz, and like I think it got to like 70 degrees Celsius. My last setup got to about, well, my current setup got to about 63 degrees Celsius, so it's definitely a lot better. It doesn't crash at 5.75, but I'm not sure at 5.85. Here's my current temperature. Here, get rid of that. Display capture? No, display capture? Is that display capture? You gonna do that? Die temperature 21 degrees Celsius. Core temperature is basically like almost 0 degrees Celsius. I'm pretty sure the coolant temperature is probably about 0 degrees Celsius. I don't have a way to measure it because even if I use a thermal camera, I actually have a thermal camera. It has thermal noise, so it's not exactly 100% reliable. But yeah, it should be lower than whatever that shows on the software. So there's that. I'm gonna put the camera back on and pray to God that whiteboard shows. All right. So thermoelectric cooling. How the fuck does that work? It's like dark magic. Assume that. I'm not sure if that shows on the camera very well. That's a hot side. That releases heat. Yay. And that's a cold side. Okay, that's actually, I need room to draw stuff. Yeah, that's the cold side. Actually, it's a lot thinner than this in reality, unless it's like multi-staged. We'll go on that later. So that's cold side. Well, this absorbs heat, so I'll also draw it like this. Because we're talking relative position. So, what goes in between here? That's a really good question. It's actually transistor junction. PN junctions. If you don't know what a PN junction is, I suggest looking up how a diode works, cause it'll probably be the best way to tell you what this thing is. We got a PN junction like this. I don't know, kind of like this. It's actually not really this, but I'll give you a good idea. Each time current passes through these junctions, because of how transistor works, it creates a voltage drop. That's my understanding of how these work. It creates a voltage drop, which means a current difference, and that current difference actually creates a temperature difference because you're creating an energy difference between two junctions. That's essentially how thermoelectric cooling works, without invoking any kind of equations or whatnot. It's a lot more complicated. Even the material of this actually determines the real cooling efficiency. Obviously, if it could be made out of anything, we could probably discover that thermoelectric cooling is base way to cool everything right now, but it's not. So that's how that works. On an actual product, it looks like this. This is also scaled up, so I can draw better. B plus, A minus, ground. You give energy here, magic happens, which I explained. It goes to ground, eat that, absorb from whatever the cold side or whatever the hot side is relative to your position, and then it gets released. And on my actual setup, you got this. Oh, okay, this might be too big, but I don't care. You got this block, you got peltiers like this. You get another block. That goes to CPU. And you got a pump. And that goes back to the cooler. And this, obviously, is a heat block. I suck at my handwriting sucks, unfortunately. This also has a pump, because, like I told you, this is a water cooler. If you don't have a working pump, your heat's gonna build up and nothing good happens. So there's another pump. That's actually kind of hidden, but I'll show it later. It's just a 12 volt, what was that called? Brushless DC pump, and seems to do a pretty good job. It doesn't create enough pressure because I tried that with my other setup when I showed you before, and it actually gets temperature worse, even with same power. That's probably because the one I have right now using is a diaphragm pump, so that creates more pressure compared to just spinning a brush and just pray to God whatever that coolant goes. But it looks like it seems to do that job for my radiator side, so that's good. Anyways, so the pump is here. I probably should have drawn it like this. This is not how, actually, you know what? Here. And we're gonna redraw that. Conventional engineering says input goes here and output goes here, but we're gonna have to break that rule a little. So I'm gonna draw another block. That's okay. You got an interconnect here, because they're connected together. This doesn't have pump here. Yeah, that doesn't have pump. But got the radiator side, going like this. Then you got this radiator. And that output of that goes back to this block. It's a heat exchanger. This is literally a heat exchanger. Hot side goes to a heat block on obviously this side. That heat gets moved to the radiator and it gets cold, like I showed before. It's literally, this is basically a normal desktop. This is how normal desktop water cooler works. And whatever cooled air or cooled coolant, I suppose, gets back to the heat block and that circulates. Thermally, this side is completely separate because that's how thermoelectric cooling works. Because of Peltier, it only rejects heat one way, from cold end to the other one, or rather PN junctions or whatever diode, whatever diode works essentially. Because diode only lets flow current one way and not the other, unless you try to blow it up. Please don't. You could blow it up if you have a electric engineering degree like I do, or mechanical. Either way. So that's how essentially the whole system works. Let me try to think whatever. Oh yeah. So Peltier inhibition and whatever yada 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 yada. Right. We gotta address that. Oh my god, this thing is really bad at raising stuff. I gotta. Alright, let me get rid of that. 1 second. I hope alcohol works. I don't know what will. I don't know what will. Okay, that's better. Good. So. You've probably seen this heard many times. Whatever XYZ company, probably Intel, I'm sure you've heard, because they worked on a thermoelectric cooler and it didn't work. They tried, it doesn't work, how come yours work? You're probably photoshopping all this. This is a deep fake, this is not a reality. That's because of how Peltier's work, they don't use phase change. Compressors and condenser, they use phase change. So they essentially store heat by changing phase. Their temperature stays the same. And that's the crucial difference. Peltiers don't do that. You could do that, but so far I'm pretty sure nobody has tried that. I'm gonna try pretty soon, but well, I'll explain that later too. So this is how Peltier works. This is something that might also use the website here. I'm probably going to have to use a website. Where's my... Oh, my cat's using bathroom and I'm live streaming. Great. Alright. Okay. This is a link. Save that right now. Alternatively, if you just look up the website, it should show up pretty right away. So, we're just gonna focus this, even though this also matters. This is how this works. Because Peltier used temperature difference as a cold side gets colder, or whatever, whichever, hot side gets hotter than cold side, whatever. That's called delta T. You get this graph. You get this kind of graph. It looks weird at first, but this will make sense. This is when this blue graph is when delta T, so the temperature between cold and hot side is exactly 0. In reality, that's not gonna happen when you start using current. But you can see that curve basically goes infinite as when current gets pretty low. Oh, and I/Imax. So Imax is essentially the maximum rated current that Peltier has, and this I symbol is essentially the real current that you're pumping into Peltiers. Delta T2 at 10, you can see the COP drops to like 3 and 2.5 ish. It's like 2.75 at about 15% of maximum current. I've set the setting before, and it is efficient, but it's not really good at keeping CPU temperature low. So you gotta go kind of like in between 15 and 20. So like 10 and 20. So like 15. So like somewhere around here. You're not wasting power because your COP is still above 1, but unfortunately it's not at 2.5, so it's like somewhere here. And I set my power around this region, so it's like 1.5 to like 1. In reality, my delta T probably is like 1 because I've seen 20 degrees Celsius between ambient temperature and my CPU temperature, so it's probably around here. It's still not bad because we still have above 1 COP, but essentially at this point we're dumping a lot of heat. And as you get colder, that temperature difference grows and it slowly goes into poo. So that's 30. We're already hitting below 1. At 40, this is like, yeah, what are you doing? At 50, yeah, 60 and 70. 70 is like you gotta go maximum current, and it's like almost 0. I think I see a mathematical artifact here because there's like a brown dot and it's not supposed to exist there. Okay, you want attention. Yeah, he likes to do that, and whenever I try to pet him, he just runs away because he thinks I'm pissed or something. So that's how that works. So, we'll draw that in here again. Something like, or something like this. Yeah, no, it's not really like that. You got this, then you got this. I don't really even need to draw like all the graph axes because really what you need to solve is the actual difference between the graph. It's better if you see the actual values so you can see the slope of it, but yeah, or rather data point or whatever. I don't know, whatever you want to call it. Yeah. Also, this is not how that works. Yeah, I don't know about delta T being like this and that. I'm guessing that's probably because you need like a minimal amount of current to actually create like a heat rejection at 10 dT. Hi. Can I adopt that cat? No, that's nice. Oh wait, here. Something like this. Something like this. Kind of like this. More you pump more current, it kind of creates more heat difference. But if the temperature is same, as in temperature difference is 10 Kelvin or 20 Kelvin, as you put more current, the coefficient of cooling drops. Why is that? That's a really good question. Because when you put more power into the Peltier, that also creates power loss. And I'm sure if somebody is majored in electronic engineering, you should know this equation, and it's called I squared C, well, I squared R. That's same because this is a transistor. This should be saying about the same. We're not putting AC current or AC current. We're putting DC current. So this stays same. If it was AC, we would have to consider capacitance, but it's ain't. And you actually don't want to be putting AC current or PWM. I'll tell you why. So I squared R. So if you increase this is squared. So what happens if you square current? You get more power loss. So you go this poo. You go like this, you go like this, and you go like this. And then obviously at maximum delta T, as you saw in that brown graph, which looks like poo, your coefficient of performance is like right here. It's like basically 0. So it's good if you can reject all that power, but 80 watts of power on like 50 millimeter by 50 millimeter of Peltier device. Good luck extracting that without inducing even more losses. That thing's probably gonna explode. And I'm not joking on that one. No, not explode, but like probably burn up somewhere in the junction. Especially the soldering joint, because assume this is a Peltier device. That wire is actually soldered onto those junctions, so even though those junctions might stay, that wire breaks down, and that's where the failure occurs. Oh, you can't really fix it either because those things are kind of sealed with silicone. So you kind of have to break it if you want to fix that. So don't try to break those. So yeah, I square R. That's why people fail. If you put more current in this, and as there's a one Peltier, even with more junctions, aka more thermal conductivity, you're still gonna have this. I mean, if you have more junctions, it will kind of bypass it somewhat because you have less resistance. More junction means less resistance. But you still have this. That's why basically everybody using this Peltier device kind of fails. One, you don't reject heat fast enough. You're probably using a cheap ass heat sink. You're not even trying to water cool it. If you use a heat sink, that heat will build up even faster compared to using a water cooler, because think about how a CPU radiator works. Like normal air cooling, you got this CPU right here, you got this heat block, you got this dumb heat block, and then you got this another dumb heat block or copper block, and then you got this radiator fin, and then you got air going out. Oh, I should have drawn it the other way, but this is how it literally looks like on a CPU heatsink, because that's not this way. This is exhaust, so unfortunately I had to draw it that way. Anyways, when you're using a heatsink like this, that heat builds up here, it has to travel all the way up here, and then it gets rejected. If you're using a water cooler or a water block or whatever, like I've drawn, we've got this Peltier, we've got this hot side. I'm not even going to drive the cold side. We already know what the cold side is at this point. If you don't remember what the cold side is, go back in video or live stream. You've got this water block. This is thermally glued. I will show you what thermal glue I use. So far, this is probably the best method of doing it without, screwing stuff down. Probably a better way to do it, but you don't want to be doing that, especially if you're trying to cram that into a desktop. So water block that gets heated directly and that water gets rejected out to the radiator, and then you cool them normal as you do on a radiator. This is infinitely better, so please do not use air coolers when you're using a Peltier. Maybe if you're using a low current, then it's fine, but you still want to have efficiency losses. That's why everybody has been using Peltier. They are not really good at getting best performance out of it. If there's a better setup, I'm sure there's probably one, probably in a military lab or whatever, or whoever designed this better than I did. I can't think of a better way. Yeah. Oh, yeah, thermal glue. I gotta show you what thermal glue I use before I go. Let's see. That's not it. Oh, look, an actual Peltier device. Yeah, I could probably use a demonstrator. Right, at least before I go, I gotta show you guys what thermal glue I use. I could use Amazon, but I also don't wanna get doxxed. All my shopping history. All my waifus. No, I don't have waifus, but that's the thermal glue. If you Amazon it or Google it, it should pop up literally right away. Alright, so this was off the schedule, but I'm gonna take down one of those Peltiers in live. Because it is pretty cool if you look at it inside. Let me get a knife. Let me get a knife. Where's the knife? Razor knife would be nice. Oh, come on. I want to rip one of these things apart. Live. Oh, here we go. Is that better? Okay. Alright. Yeah, see how I can like cut in between here? Like it doesn't go all the way in. It's because there's actually a junction like kind of soldered in between this. So yeah, I kind of have to break it if I want to take it apart all the way, or like use a heat gun. I'm gonna do that actually. Oh, here we go. This one doesn't work. It kind of works, but there's hot spots. So, and you don't want to be having a Peltier with a hotspot. That means there's defective there junctions there somewhere. You can't really tell with the but just by testing with your hand or whatever. I mean, I'm sure you kind of could if there was enough temperature difference. But you also gonna risk breaking the Peltier device if you're doing that with nothing cooling on it. So, yeah, probably don't do that. Don't probably do that. That's the advice I could tell you. Ooh, huh? Comes off right away. Huh? Good. Oh shit. I probably don't want to bring that in. So that's what goes on the inside. Got those junctions right there. It's all parallel because it's 6 like that. And you got all those PN junctions, I guess, whatnot. Yeah. And then you got this solder wire right there. That's where usually the failure occurs, because these are kind of fine, but those wires, it's solder wire, so those solder is gonna melt, and all that power goes through has to go through that wire first. So yeah, there's an electrical bottleneck there. Oh, I gotta throw it down in the trash. Probably not normal trash because this is like heavy metal and stuff. Is there anything else I haven't covered yet? I don't think so. I don't think so. Pretty sure I haven't done anything yet. Huh. Maybe I could end the stream early because there's nobody watching. There's somebody, well, when they eventually find this on the internet. Before I go, I'm gonna probably show you that other pump as well. That's the other pump right there. You won't be able to see marking, but if you try to look up a 12 volt, there we go, shows up. Yeah, I can't show the sticker, but okay, it's kind of zoomed in. It's that pump. If you look up 12 volt brushless pump, there's like a tiny one. It says submersible, but obviously we're not submersing the pump. So I just had the input of the pump connected to one of the tubings and then output going to the radiator. Maybe I'll just show you my battery too while I'm at it. Off topic, but I don't care. This is my channel. This isn't a college. I can stream whatever the hell I want as long as it's not spooky stuff. This is a battery I'm making right now. Yeah, it has a bunch of scratch marks because I've been reusing these cells like twice at this point and I gotta take the junction off. Oh, those aren't burn mark, don't worry. If that was a burn mark, I would have been here at this point. Why am I, so that frame is 3D printed, so why do you think I'm doing that? It's because my plan to cool those batteries are, I wish I you guys this, I definitely should have done that. Using one of these cooling blocks. That's basically where the Peltier gets mounted. Either the hot side or the cold side. It gets mounted to this and then it gets glued on. I usually sit those like overnight. And it works pretty well. Yeah. Don't try to do that. That's how you actually. Did I solder the other side? I think I soldered the. I have a spot on the other side. I'm still not gonna do that though. So that's basically how it gets mounted like that. It's flush. Normal battery holding cells, they don't do that. Cell holding cells, they don't do that. It's not really flush. So I put like an insulating foam on this side. I put it has like a adhesive. And you put this on it. Put water through. I'm sure you could probably. I'm like, if it's like normal temperature, like normal is like 20 degrees, 25 degrees Celsius, you could probably cool the battery using that way just by using a radiator. But if it's above that, like 35, 40, I would definitely start cooling that with either with a compressor or thermoelectric coolers. If it's a car, you probably should be using a compressor because you have more space to do it, but if it's like a motorcycle that I'm building right here, you don't really have a room for compressors. So that's why I use these. Put this on here, put water through it, you stack it, have water loops, and then it goes thermoelectric cooler. Heat exchanger thing happens, and then you cool the battery. Literally same thing, just, yeah. I have one viewer, but unfortunately I'm about to end the stream, so you'll have to watch that video, which will not be pre-recorded. What else can I show you? Here. I just wanna do the sake of proof that the system's not gonna crash. So, oops. I'm gonna play Kerbal Space Program live. Video capture. Yep, hide that. Steam. Oh, well, that guy left quickly. Whatever that was. Oh, Core 7, they hit 1.344. That's, I think the safest maximum is about 1.35. That's not good. Temperature's mostly stable. Hasn't hit, oh, it has hit 4.5, 4.9, 4.6. Seen it hit like 4 degrees Celsius, so the temperature definitely hasn't gone off. Yeah. Here, I'll play Kerbal Space Program for like 2 minutes and then I'll end the stream. Just as a proof of concept that this actually works. I haven't done a stability test, but that only seems to be like 100 watts. I've seen this thing pull 150 watts on a benchmark, so there's that. Oh, my views went up by 3. Except I don't see anything on graph. Yeah. Wait for program to load. It likes to do that. It likes to do that. I don't think I've even loaded KSP on with this value. So this will be interesting. This might actually crash my computer, and I'm not sure exactly what happens if my computer crashes while I'm live streaming. Hopefully this entire thing doesn't disappear. You know, go like this. Oh wait, is that the same? Yeah, that's same monitor. Oops. Alright, we're gonna see if this computer tried to crash. You should probably looking at the temperature and the core VID. Oh, that just hit 1.34 volts. I'm not sure when. If that starts going over 1.5, we're in spiky territory. Because I'm pretty sure according to Scatterbencher, like the safest voltage range that you can have in a normal setup, normal water cooling setup, is like 1.35. I'm not sure if that was AMD blocked or whatever. I think GamerNext was they use a PBO. So I think you could probably break that. I mean, I've seen this thing use like 1.38 volts on my normal AIOS cooler setup. Let's see. I have an FPS counter. Probably can't see that though. Let's see, will this thing crash? Will this thing crash? That would suck if this thing crashes. FPS counter is at 28, 27, 28.8. I used to get around 25 to 24 at 5.75 ish. So this is definitely improvement. And yeah, this is my base. Let's see, what's my thermal like? Hmm. 38. That's definitely hotter than before. Yeah, that's definitely hotter than before. Core temperature's still pretty good. The die temperature's hot. I mean, this is definitely cooler than basically everybody's water cooling setup, so there's that. And no, this is not liquid nitrogen. Core 1 utility 94, Core 2 86, Core 3 68. So this is about like, how much CPU am I using? 62, 54, 52. So about half. Yeah. Oh, that CPU power, it actually went up to under 50. I'm pretty sure I saved that here too. Did I save it? I hope I did. Here. I'm pretty sure I did. Ah, here we go. Yep, 152 watts. You're never gonna see that on a 9800 X3D unless it's like really overclocked. Yeah. Well, I'm gonna end the stream at this point. I am going to end the stream at this point. Hope you learned something by watching this. I hope more people use this Peltier devices. If you watch this back to back, you should already know how Peltier device works without, having to know physics. So hopefully somebody comes up with a better Peltier device or Peltier cooling setup than I am. If nobody does, then, well, alright. Have a good night or have a good day.